Section 7.1, Trigonometric Identities. It's a fairly long assignment from the book because there are many different techniques for working with these identities, so just need a lot of practice. Okay, so before we get to identities, we're first just going to review what an equation is. And this is as simple as it sounds. An equation is something that has an equal sign in it. So just to be totally clear, this right here, we'd say this is an expression, but it's not an equation because there is no equal sign. This next one, there's an equal sign, no equal sign, so that's not an equation. Here's an equation, I see the equal sign and another equation. Okay, so just equations better have an equal sign. Okay, so identities are equations that are true for all values of the variables in the equation. Okay, so is this an identity? Not even in the running, because it's not even an equation. So no, that's not an identity. Is this an identity? Well, it is an equation, but is it true for all values of x? No, certainly not. In fact, I think it's only true for x is 2 and minus 2, so that's not an identity. This next one, again, it's an equation, there's an equal sign, but no way is that an identity because it's not true for all values of x, y, and z. Again, this is kind of a freebie here. Sorry I got so negative. This one isn't even an equation, so it can't possibly be an identity. Okay, here's another example. This one was an equation, and yes, this is an identity. This is true for all values of a and b. Okay, last one. This is also an equation. I see the equal sign, and it is an unfortunately common mistake to view this as an identity. It is not an identity. So I'm going to put in no. Yeah, again, a lot of no's. And one way to see that this is not an identity is, for example, the number a equal 1. Right? The left-hand side would be 3 squared, which is 9. But the right-hand side, again, when a is 1, would be 1 squared plus 4, which is 5. Right? So this equation is not true for all the values of a, therefore it's not an identity. Okay, so I actually just did what I have in the notes here. In order to show that an equation is not an identity, all you need to do is find one particular value for the variable that doesn't work. That is, that makes the equation false. So what did I do? I just picked a equal 1 to show that this was not an identity, but I could have just as easily picked the number a equal 3. Okay, so 3 plus 2 squared is 25, but on the right-hand side, if I square 3 and then add 4, I get 9, 13. It certainly was easier to pick a equal 1 than 3, right? Because 25 isn't equal to 13, this equation is not an identity. Okay, so this section is about looking at trigonometric identities. And we've seen most of these before. These are identities, that is equations that are true for all values of the variable. And they involve trigonometric functions. So this grouping here, the reciprocal identities, sometimes we view these as simply definitions for secant and tangent. These are the ones that we use most commonly. The Pythagorean identities, we've seen these before. Even and odd identities, we saw that last chapter. Sine and tangent are odd functions, cosine's an even function. And then identities that we haven't seen yet, and in fact, I don't think we're going to wind up using them in this section. They're just in this table for sort of completeness, and we won't even prove these until next section, 7.2. Okay. All right, so what we're going to do with these identities, a couple things. The first is we're going to learn how to simplify trigonometric expressions using some of these trigonometric identities. So we'll have some expression and involving trig functions, and we'll try to simplify it. And we'll have to use all the tricks that we already know about factoring and getting common denominators and so on, all the algebra skills we already have. But then in addition, we're going to use the trigonometric identities that we just looked at to try to simplify things. Okay, so just a quick review of these, what our book calls special product formulas, this idea that we'll need to perhaps factor or expand things. So some algebra skills here. And really, I don't think we'll look at 4 and 5 here, but just 1, 2, and 3, these algebra identities that we need to know about. Okay, so let's do a couple of examples. So here's a trigonometric expression, and the title here is that we're going to try to simplify this expression by rewriting trig functions in terms of their sine and cosines. So if we're going to simplify this, well, we could rewrite tangent in terms of sine and cosine. So we get cosine t plus, this is tangent is sine t over cosine t, and then sine t. So I'd like you to get into a habit of trying this 2-column format where you make a change to the expression and then explain what the change was here. So this was the, I guess this was a reciprocal identity. Reciprocal identity is what our book calls it anyway. That tan t is equal to sine t over cosine t. Okay. Okay, the next step here is an algebra step, and this is to try to get a common denominator for these two terms. We've got a fraction here, and so we can bring the two terms together by getting the common denominator of cosine. So this will be, oops, gotta find home row, cosine t over cosine t, and then, sorry, cosine squared over cosine t. I'm taking cosine and multiplying top and bottom by cosine. And then this next one, this is sine squared t over cosine t. And we put these together in a common denominator. The denominators are equal, so now we can combine the numerator. And this is all over cosine t. So we probably could have done that in one step. So this is common denominator. Common denom. That's enough. Common denom here too. And then in the numerator now we have cosine squared plus sine squared. And this is the point where we're using an identity. This is the Pythagorean identity. So Pythagorean identity, one of the three listed for our book. And then lastly, as a final simplification, we can write that this is secant t. 1 over cosine is secant. And I guess that would be another reciprocal identity. Ooh, gracious. Okay, we'll try one more. We're asked to simplify tan squared minus secant squared x. Okay, so again, the strategy here is going to be simply to replace trig functions in terms of sine and cosine. So tan is sine x over cosine x, and that's squared. And then secant is 1 over cosine x. And this replacement, we're talking about replacing, but again, those are the reciprocal identities for defining tangent and secant in terms of sine and cosine. Okay, let's just get a common denominator now. Downstairs we have cosine squared, so we can combine the numerators. The numerator of the first fraction is sine squared, and the numerator for the second fraction is, well, I guess is 1 squared. And downstairs we have cosine squared x. Okay, so common denominator. Then made, or it didn't take that long to type that out. Okay, so this simplify, sometimes it's hard to know when you're done, when you're asked to simplify things. I think there is another step to go here. If in the downstairs we were to replace cosine squared, and there's more than one way to get the simplification, but this is what caught my eye first, is downstairs we can replace cosine squared with 1 minus sine squared x. And this is the Pythagorean identity again. Okay, so lastly, what I see now is that the upstairs is the opposite sign from the downstairs. Maybe I could do that in 2 steps. I don't know if this would be more, excuse me, more helpful or harmful to do it this way, but upstairs I could factor out a -1. Nope, it's going to be more harmful, I think. And then downstairs it's the same. All right, so the thing in the parentheses, they're in reverse order, but it matches the thing in the denominator, and they are parts of products, so we can cancel. So this is a factor step. So again, a lot of algebra techniques that you know are coming in here. Cancel. So yeah, this expression simplified dramatically. It was actually always equal to -1. Okay. All right, so the heading that we were just looking at there was the idea of replacing for example, tan and secant in terms of sine and cosines, and then looking for cancellation. Sometimes you can also do replacements using other Pythagorean identities. So this is the exact same problem that we were just looking at, and instead of replacing tan and secant with sines and cosines, there's another, perhaps much faster simplification that can be done now. So you know, hopefully you'll have this table available sitting next to you when you take your exam. So you'll have all of these identities right at hand here. And what you might see to do here is to replace secant squared with 1 plus tan squared. And this will lead to a simplification much more rapidly than our last one. So secant squared x, and then minus, now we do need the parentheses here. We're replacing secant squared with tan squared x plus 1. And this was Pythagorean. It's listed as a Pythagorean. And now we're just going to get some cancellation. You have to certainly remember to distribute the minus sign, so tan squared minus tan squared, but then also minus the 1. I don't know what to call that. I will just kind of generically say that's algebra. Oops, I missed my 1. Okay. There are a couple of other algebra skills that you might need a refresher on. Well, I guess we've done this one already, the common denominator. But this one's a little bit more difficult. The denominators look so different. So to get the common denominator, we're going to use the product of the two denominators as the common denominator. That is, the first fraction, we're going to multiply top and bottom by 1 plus sine t. So if we do it to the bottom, we certainly need to do it to the top so we get equality. And for the other fraction, we're going to multiply top and bottom by 1 minus sine t. Oh, this font looks so small here. I wonder if I can bump it up just real quick. 150. Okay. Right, top and bottom. Oops. Right, and this is common denominator. Okay, so the denominators are equal, so now I can add the numerators together. So when I add the numerators together, I get 1 plus 1 and sine t minus sine t. So I get 2 in the numerator. And downstairs, this is one of the special products that we reviewed here. This is a minus b times a plus b. So downstairs, I get that this is 1 minus sine squared t. And I'm going to list out my reason here with this special product reminder. This is a minus b times a plus b is equal to a squared minus b squared. Okay, and then downstairs we get another simplification, 1 minus sine squared, that is cosine squared t. And this is the Pythagorean, or one of the Pythagorean, I should say. And then lastly, we can write that this is 2 cosecant squared t. For me anyway, I'll say that this is optional. I don't usually, oh, beg your pardon, I messed that up. This is secant squared, and I don't know what I was thinking here. And I would like you to always remember that 1 over cosine is secant. Okay, try one more. So another algebra skill that maybe needs a little rust remover on it is trying to simplify something by multiplying by a conjugate. Now, a lot of times this happens when we're working with square roots, but here we don't have a square root. But in any case, a plus b and a minus b, these are called conjugates. So whenever the sign switches on this sum, the things are called conjugates of one another. So this is sometimes hard to do on your own. Sometimes I might give you a hint to consider doing this, but just to see how this helps, we're going to simplify this expression by multiplying top and bottom by the conjugate of, in this case, the bottom. So this means we want to multiply by 1 plus sine of t. And we want to do that both top and bottom. Right? Otherwise, we wouldn't have equality. Okay. So this is algebra. I mean, we're multiplied by 1. It doesn't change our fraction. Okay, so upstairs, what do we have? We have cosine squared t and 1 plus sine t. Downstairs we have 1 minus sine squared t. Again, that's the same reason as it was up here. This is one of the special products. A minus b times a plus b, we get the a squared. 1 squared is just 1, so we don't have to write that out. And now, again, the 1 minus sine squared is simplifying down to cosine squared. So one more here. I'll do a copy paste on it. This downstairs is cosine squared. And this is Pythagorean. And then we get a final cancellation here. We've got a product upstairs and a product downstairs, so the common factor can cancel. Okay, I think I better put in a timestamp. We are at 19 minutes. Okay, so what we did in that section was trying to simplify trig expressions, and now we're going to do something slightly different. We're going to look at proving or verifying a trig identity. We've got a long list of trig identities already given to us, but we're going to try to extend the list by proving additional identities. So remember, to show an equation is not an identity, all you have to do is find a single number that doesn't work in that equation. I bring up that reminder just to try to tell you that on the flip side, if you're trying to show that something is an identity, it's not adequate simply to find a value that does work. Right? Instead, what you have to do is start with one side of the identity and transform it, or perhaps simplify it until it becomes the other side of the identity. Sometimes the other side isn't any more simple, so we should just say transform rather than simplify. Okay, so do a couple of examples here. So we're going to try to prove that this equation is an identity. That is, that it's true for every value of t. So what we're going to do is start with one side of the equation, the identity, the thing that we're trying to show is an identity, and manipulate it, or simplify it, transform it until it becomes the other side. And as a general rule, it's usually best to start with the side that's more complicated. And here, that's the LHS, the left-hand side. Okay, so we start with the left-hand side, and now we're going to change it. Right, so how are we going to do that? Well, one strategy that we've already talked about is the replacement of, in this case, tangent with sine over cosine. So this is reciprocal identity. That's what how tangent is defined. And then this is, I don't know what to call this. I think I'll just generically label it as algebra, flipping that downstairs fraction over algebra. And then we get a cancellation here. The sines are going to cancel, and this becomes cosine. And this is a cancel. And that's done. Maybe I'll just go ahead and that's the right-hand side. So we have verified this identity essentially just by simplifying the left-hand side until it became the right-hand side. Okay, so that was not the most difficult one you're ever going to be asked to do. Here's one that's certainly a little bit more difficult than the one we just did. Okay, so sine 3t plus cosine 3t quantity squared is supposed to be equal to this right-hand side. And again, we're trying to show that this is true for every single value of t. Right? The way we do it is start on one side, the more complicated side. I'm going to say that's the left-hand side, maybe because of the squaring. And we're going to try to transform this left-hand side until it turns into the right-hand side. Okay, so this is sine squared 3t, can't find my t, plus twice sine 3t cosine 3t, well, this is going to be a long one, and then plus cosine squared 3t. And this is the special product. Maybe we could call this FOIL, but I'm going to call it special product. This is the a plus b squared equals a squared plus 2ab plus b squared. Okay. What we have now is, and should I rewrite it? No, I'm not going to rewrite it. I'm just going to use it. This is 1 plus twice sine 3t cosine 3t. And this is the Pythagorean. Maybe I should have regrouped this, but what we see here is that we have a sine squared and a cosine squared 3t. So I'm going to go ahead and write it. This is because sine squared x, doesn't matter what the x is, so it's totally fine that in this case the x is 3t. So that identity tells us that sine squared 3t plus cosine squared 3t is going to equal 1. Oh, and look at that, we're done, because this is the right-hand side. Okay, so sometimes if you start on what you think is the most complicated side and work for a while, pause this. Yeah, I had a copy paste fail to edit moment here. So the left-hand side of this proposed identity looks more complicated. I'm going to start with it and try to simplify it. But if you don't reach the right-hand side with your simplification, sometimes what you have to be prepared to do is start on the right-hand side then and see if you can work your way to the middle. So we'll do this as an example. Right? So we could break this down into sines and cosines. That's a definite possibility, but it might be best to employ the Pythagorean identity that relates tangent squared to secant squared. Okay, so I think I know what it is. I know I could derive it, but just for speed here, I'm going to go copy it or look at it again. Right, so the tan squared, this is the one that we're going to use. I hope this is not taking too long. Shoot. Sorry, stop scrolling. So this is the trig identity that we're going to use here. So the tan squared is equal to secant squared minus 1. So we can just flip that around. So this numerator is secant squared t minus 1. Now the identity is written with an x, but it applies to any argument there. Okay, downstairs this is secant t minus 1. This is a Pythagorean. Okay. Upstairs we now get a factoring. This is secant t minus 1, secant t plus 1. And this is the special products formula. It's a special products formula sort of run in reverse, though. This is a minus b, a plus b. And now upstairs we have a product, and downstairs a product. It's hard to call it a product, but this times 1 maybe, but we can cancel. Sorry, this is not quite the example that I thought it was, because we successfully reached the right-hand side. Oh, maybe I had thought about using sines and cosines instead of using the secant. Sorry about that. Okay, if we had not come all the way to the right-hand side, which we did, we're done, then we might have had to pick up on the right-hand side and try to work back. All right, sorry about that. Right, the one thing that you might be tempted to do, but you have to resist this temptation. If you are asked to prove an identity, do not start with writing that identity down and then manipulating both sides of the identity. If this is an example we've already done, but if you presented your answer in this form, you would get only 6 out of 10 points. Right? We simply will not allow this to stand as a proof of an identity. Right? So just to review, this is I won't put in the reasons again, we've already done this one. You start on the left-hand side and you go until you get to the right-hand side, and then you get 10 out of 10. Right? Why are we so picky about this? Well, here's an example. Perhaps example is so obvious that it doesn't seem like it merits anything, but I just want a quick answer here. Minus x equal x. Is this an identity? The answer is no. E.g., take x equal 3. Right? Negative 3 does not equal 3. That is not an identity, minus x equal x. That's not true for all values of the variable. Right, but look what happens if we do an algebra step. If we square both sides, negative x times negative x is x squared. So this is an identity. I mean, clearly, the two sides are equal no matter what the value is. So the point is, ending with an identity does not show that you started with an identity. And that's the argument that was presented here. The student said, well, I ended with an identity, therefore I must have started with an identity. And in this particular case, it happens to be true, but this is supposed to be the example that tells you that line of reasoning is not valid in general. Okay, looks like a long day today. We are at 30 minutes. I guess that note on grading is very short. So, in your calculus class, you will need to do this technique. What you're trying to do is eliminate square roots using what will be called a trigonometric substitution. So the good news here is that when you have this square root expression, you're going to be told exactly what substitution to be made. In particular here, the instructions are in this square root, I want you to replace the x with sine t. In your calculus class, you're typically going to have to figure that out on your own. What substitution do I need to make here in order to get rid of the square root sign? Okay, so we're just following the instructions. They told us to replace the x with sine t. That's what we did. And now we're going to try to simplify. Okay, well, this does simplify. The 1 minus cosine squared, sine squared is cosine squared. Okay, and then this other little bit about what's going on here, they tell us to assume that the angle is between 0 and pi. And what that means is that the cosine is going to be a positive number. So when we take the square root of cosine squared, it could be either plus or minus cosine, but here we choose the cosine of t because of the t values that we were told about. The t is somewhere between 0 and pi over 2. All right. I guess we'll try this one last one. Again, right. So the point here is this substitution has eliminated the square root. Now we have an expression that no longer has a square root in it. And in your calculus class, it'll be much easier to use this expression without a square root. All right, so I guess we're just trying one more here. So this awful expression that's got a square root in it, we're told to make this substitution and try to simplify. Okay, so when we make this substitution, we replace the x with 2 tan t, replace this x with 2 tan t. Boy, it looks awful. We're trying to simplify though, so let's give it a go. Outside this would be 4 tan squared t. Square each term separately there. Ooh, and I'm still in the denominator. Inside I get 4 tan squared t plus 4. Right. One more here. I'm going to try to get this. 4 tan. I'm just going to recopy that thing. But underneath the square root, I see something special happen. The 4 is factoring out. Tan squared t plus 1. And 4 was common to both terms there. And I haven't been writing my reasons the way I should, but I'm going to try to finish up here quickly. This is a Pythagorean identity then. This tan squared plus 1, that's secant squared. Got an extra set of parentheses there. Okay. So we're taking the square root of 4 and the square root of secant squared. All right, so that's going to simplify down to 2 secant t. Again, the restriction on the values of t have it arranged so that secant t for this interval of t is a positive number. Okay, I guess there probably is a little bit more that we could do here if we switch to, I don't know what to do now. I would probably just switch to tangents, sines and cosines at this point. So this is 4 downstairs. This is sine squared t over cosine squared. Oh shoot, my typesetting's going to go south now too. And then this is 2, 1 over cosine t, a horrible compound fraction here. Okay, so things that are in the denominator downstairs are going to flip over and go to the numerator upstairs. This is going on too long. Okay, so the upstairs we're going to get a total of cosine cubed t, and downstairs we are left with, it looks like 8 sine squared t. And I think I'll quit there. There's a possibility we could rewrite this in terms of cotan or some other thing that would make it look simpler, but that'll be enough. Okay, so note on the grading, when you're asked to prove an identity, remember that in some ways you are essentially being given the final answer. The very last thing that should appear on the paper is this connected identity. So you have to make sure you understand that when it comes to grading a problem like this, it's not enough that you simply started on the left-hand side, did a bunch of really hard to follow, illegible stuff, and came to the right-hand side. That stuff in between needs to be very clearly presented. So show a lot of steps. Don't cross things out and make them hard to read. Try to give reasons for each of your steps, and then you'll be sure to get full credit. Okay, that's it for today. We'll see you in section 7-2.